Hello. Now we are going to look at how we can use sample spaces for probability. So first, what is a sample space? A sample space is just a list of all of the possible outcomes in a particular situation. So we'll get a description of the situation in a question, and all of the things that can happen is called the sample space. So all of the different outcomes we could get. So if we take a particular situation, if we flip two coins and we could get a head or a tail on either of the coins, if we flip two of them, what's all of the things that can happen? Well, that would be the sample space for that question. So we could get a situation where we get a head on the first coin and another head on the second coin. That's a possible outcome for this situation. Or we could get a head on the first coin and we could get a tail on the second coin. You can see how I'm writing these. I have my brackets. They look a bit like coordinates. Or I could get a tail on the first coin. I've run out of the situations where I could get a head on the first coin. So I could get a tail on the first coin, and then I could get a head on the second coin. Or I could get a tail on the first coin and a tail on the second coin. And those are all of the things that could happen when I flip two coins. I could get a head and a head and a tail and a head, or a tail and a tail. And I've now covered all possibilities. So that's the sample space for the question. If I want to talk about different things that can happen, it's going to be one of the things on this list. I can use something called a two-way table to keep track of this information. So this is quite a short list, but the list can get very big. So it can be useful to have a tool like a two-way table that keeps track of what it is I'm talking about. So what I've got is the outcomes for coin 1, the first coin that I have listed here. And coin 2 is C2, is the head and the tail that I could get for my second coin. So the way I'd use this is, here I got a head on the first coin, and I got a head on the second coin. Here I got a head on the first coin, so I'm reading across this way. I've got a head on the first coin, and I got a tail on the second coin, and I got a tail on the first coin here, so tail for the first coin, a head on the second coin, and here I got a tail on the first coin, and I got a tail on the second coin. So this table allows me to create the same list, but if the list is quite big, it's easy to miss something if we don't use a structure like this. We can use these lists to figure out what the probability of something happening is. So all of these events are equally likely. So we're able to say the probability of getting two tails. So what would be the probability of getting a tail and a tail? Well, there are 4 total possible outcomes, and I only want one of them because there's only one time that I get a tail and a tail. So that would be one outcome that I want out of the total number of outcomes, which is 4. So there's a probability of a quarter of getting 2 tails when I flip my coins. We can take a more complicated situation here where we have 2 spinners are spun. Now, we can get these fairly frequently in exams, and I'm just going to explain what they are supposed to be. They're effectively a spinning top. The idea is you have a piece of card. In this case, they're squares, but they could be triangles or lots of different shapes. And you would punch a hole in the center of your piece of card, and you'd push a pencil through it or a pen through it, and then you'd be able to spin this like it was a spinning top. And where it lands on the table when it falls over, so we set the spinner spinning like a spinning top, and it has to fall over on one of these sides. Whichever side hits the table, we take that number as being the outcome. That's what a spinner is. So it's just a spinning top with numbers on its sides. Now, what is the sample space for this? Well, if I want to describe this situation, I'm going to say that this is spinner 1 and this is spinner 2. So the sample space is just listing all of my possible outcomes. I've called this spinner 1, so I'm going to take these as the first outcomes, and then what can happen with the second spinner as my second set of outcomes. So I could get a 3. It could land on this edge or this edge, and I'd get a 3 for my outcome on my first spinner. And then I could get a 1 on my second spinner. It could land on this edge, or I could get a 2 or a 3 or a 4. So I need to run through all of those possibilities. So a 3 on the first, a 2 on the second, a 3 on the first, and a 3 on the second, a 3 on the first, and a 4 on the second. Or I could land on these two edges for my first spinner, and I could get a 4 on the first, and a 1 on the second spinner, 4 on the first, 2 on the second spinner, 4 on the first, 3 on the second spinner, or I could get 4 and 4 on both spinners there, on these edges, on that edge. So those are all of the different possible things that can happen when I do out my experiment. So spin this spinner, and then all of the different ways that that can play out are listed in my sample space. I can use a two-way table to keep track of that information more effectively. Already this list is getting a little bit annoying. It's quite long to try and read through. The table gives me more structure so that I don't make any mistakes. And it works the same way. The spinner 1 outcomes are listed here, and I've labeled it as S1 for spinner 1, and the outcomes for spinner 2 are listed here, and I've called that side, the top of it, being S2. So I'm going to have outcome 3 on my spinner 1, and I got a 1 on spinner 2, and I fill all of that out just like I did before. So 3 on spinner 1, 3 on spinner 2, 3 on spinner 1, because I'm reading across this row here, and down column here will be outcome number 4 on spinner 2, and then outcome 4, or get a 4 on spinner 1, get a 1 on spinner 2, and we keep on going up through, and now we have all of our outcomes listed, and our table means that we can very clearly see that we haven't missed anything. If we lay our table out correctly, it's impossible pretty much to miss a possible outcome, which is an advantage over just starting our list. Now, if we are structured in the way we write our list, it's pretty good. We are unlikely to make a mistake, but the table is even more reliable, and we can be directly asked to use a two-way table. Now, based on our sample space, what's the probability of getting two even numbers? So probability of even and even on our first spinner and our second spinner. So what outcomes meet that criteria? What outcomes would we be happy with in that situation? So we have to get an even number on both of our spinners. So 1, 3 definitely doesn't work. 3, 2 doesn't work. 3, 3, 3, 4, 4, 1 doesn't work. 4, 2, that one works. I'd be happy with that. I have a 4 and a 2. They're both even numbers. 4, 3 doesn't work. 4, 4 does work. So 4 out of my 1, 2, 3, 4, 5, 6, 7, 8. 2 out of my 8 outcomes would work. So I'd be happy with 2 out of my 8 outcomes. So 2 out of my 8 outcomes I would be happy with. So that simplifies to a quarter. A quarter of the time I would get what I want. So a probability of getting two even numbers would be 2 out of 8. And I can see I have 2 outcomes here and 4 outcomes here. In total I have 8 outcomes. And I can do that by saying 2 by 4 would give me 8 total possible outcomes. Now this is one way of doing a two-way table, but we can also be asked to do a two-way table where we add the results of our outcomes together. This is a common way to use a two-way table that's a little bit different, and it means a two-way table is even more useful because it's quite difficult to do this just from a list. So in this type of two-way table, we're told that we have to add the results of the spinners. So my outcome here is no longer 3 and 1 because I'm supposed to add those outcomes together. So I'd have an outcome of 3 and an outcome of 1. If I'm adding them together, I put a little plus sign here to remind me, 3 plus 1 is what I'm doing. And I just end up with 4. So the outcome here is now just getting a 4. So in total my score was 4. Now we don't need to write this in all of the time, but you can if you have space and you would like to keep that structure, but it's easier to read if you're comfortable with doing the addition in your head or on the calculator. So we have 3 and 2 was the outcome here, so we'd add that together and we'd get 5. 3 and 3 would give us 6. 3 plus 4 is going to give us 7. Here we have 4 from our first spinner and 1 from our second spinner is going to be 5. 4 and 2 is 6. 4 and 3 is 7. 4 plus 4 is 8. And now this is how we can get a two-way table where we've added the results of our spinners. So based on this now we can be asked different questions. What's the probability of getting an odd number? So these are now our outcomes. What's the probability of getting an odd number? So we go through and we see, well, what odd numbers did we get? Well, we got 5, 6 is even, 7 is odd, 5 is odd, 6 is even, 7 is odd, 8 is even. So we got 1, 2, 3, 4 out of our 8 possibilities were odd. So I can say that I have, get rid of them, I have 4 out of my 8 possibilities I would be happy with, and that simplifies to half of the time. So half of the time I would get an odd number. So that's my answer there. I would go through and I would underline all of the outcomes that were relevant to what I was doing. And then I would say, well, I have 1, 2, 3, 4 out of a total of 8 possible outcomes that I would be happy with. So wanted over total is how I get my probability. And then I say that that's going to be equal to a half. And then finally, what's the probability of a number greater than 8? So what would be the probability of getting an outcome that was greater than 8? So I go to my table, and I'm not interested in my odd numbers anymore. So I go to my table and I say, well, what numbers in my outcomes, my possible outcomes, are greater than 8? So none of them, because 8 is not greater than 8. That's the only one that even looks like it could work. But 8 is equal to 8. It's not greater than 8. So none of my possible outcomes I would be happy with. So it would be 0 out of 8. There's no outcome I'd be happy with. So I just say the probability is 0. I definitely can't get a number greater than 8. So its probability is 0. And that is how we can use our sample spaces and our two-way tables for solving probability questions. And that is what we need for now.